Hello, I'm Mr. Howard. In this video, this is part 3 of our first look at polynomial functions, and so far we have discussed how to identify a polynomial, how to identify the degree of a polynomial, and then how to identify the roots, what type of roots, and the end behavior, and then make a sketch. So we're going to continue that in this video, but we're going to work two examples in this case that are a little different than we've had before, because we're actually going to have to do this step 1 first. We're actually going to have to factor them. They are not, our examples now are not already factored for us, so we have to do the factoring and then continue the process. So we have x cubed minus 3x squared minus 36x plus 108 for my students. That's number 9 on the assignment portion of lesson 1. And you see that we have 4 terms here. Well, think back to your practice in factoring in Algebra 2. Possibly in Algebra 1 you did factoring by grouping, but certainly in Algebra 2. And when we have 4 terms, generally that means that we are going to factor by grouping. So in looking at this, we are going to group these 2 terms and these 2 terms together and start by taking out a greatest common factor. So the greatest common factor of this portion right here would be an x squared. So I'm going to rewrite this over here. We're going to factor out an x squared, and we would be left with an x. If you factor out an x squared from x cubed, you're left with x. And then we would be left with minus 3. If you factor out an x squared from minus 3, you're left with minus 3. And then we would have right here 36 will actually go into 108, so I'm going to factor out a negative 36 here. So a negative 36 is being factored out now, and you factor out a negative 36 from negative 36x, and you're left with just x. You factor out, and you might need to do this in your calculator, but if you factor out a negative 36 from 108, you would be left with negative 3, x minus 3. And that's good because, remember, in factoring by grouping, we want the same factor to be in parentheses in both places, and we have that. And then we just pair, we take x minus 3, we write that once, and then we pair the stuff that's outside the parentheses together in its own set of parentheses. So to shorten that up for you, here's what it's going to look like. We're going to have x squared minus 36 in one set of parentheses. What order we write it in as far as which set of parentheses goes first doesn't matter. And then we have the x minus 3 just one time. You don't write it twice, it's just once. X minus 3 in its own set. So we could have written it x minus 3 times x squared minus 36, and that would have been fine. But this also works. Alright, so our next step is to look to see if we can factor it anymore. And we actually can, because x squared minus 36 is a pattern, hopefully, that you remember, and that would be the difference of 2 squares. So that's going to be x plus 6, x minus 6, and then we still have that x minus 3 left. So here is this thing completely factored down, and we have completed step 1 because we have it completely factored. Now we can identify the roots. So the roots are going to be, that means that we set this whole thing equal to 0, and either x plus 6 is 0, so x plus 6 has to be equal to 0, or x minus 6 has to be equal to 0, or x minus 3 must be 0. In order, when you multiply 3 terms, if the whole thing is equal to 0, then at least one of these terms has to be equal to 0, because anything multiplied by 0 is 0. Okay, that's why this works. So x plus 6 equals 0. We solve for x and we get x equals negative 6. So that's a single root, right? Single root. This has an implied power of 1 here, an implied power of 1 on that parentheses, and an implied power of 1 on that parentheses. So these are, all 3 of these are single roots. So a single root at x equals negative 6. We solve for x here and we get x equals positive 6. So we have a single root at x equals positive 6. Solve for x here and we get x equals 3. So we add 3 to both sides to get this, of course. X equals 3 is another single root. So we have 3 single roots. All right. So we've identified the roots. Now, including the type of root, we've done that. We've got 3 single roots, so that's done. Now we need to identify the end behavior. For that, we're going to go back up to the original function where it's completely unfactored here, so it's expanded all the way out. And we look for the highest exponent, the largest exponent, and that occurs right here. That's a 3, so we have a degree 3 polynomial, and that cube term here is positive. There's an implied positive here. It's positive, not negative. So that means it's going to have this type of end behavior. Like the cubic parent function, it's going to have end behavior like this. So as x approaches infinity, it's going up to the right, and as x approaches negative infinity, it's dropping, so it's down and to the left. Okay, so that's what our end behavior looks like. So we'll just make a note of that like this. So that's what our end behavior looks like, up and to the right, down and to the left. So that part's done. Now we just need to graph it. All right, so this is pretty straightforward now. We've got this pretty well done. So let's just put our roots in there. So we have a single root at -6 out here. So single, we need to label this single at x equals -6. It's going to be right there. We've got a single root at, let's just go in order looking at this. So x equals 3, so about right here. And I'll label that in a second because we need to see how our graph is going to come in there so we don't get in the way with these labels. And then we have a single at x equals 6. Alright, so we can see how our roots are going to be. We know that our end behavior looks like this up here. So over here on the far left side, as x approaches negative infinity, I am dropping, I'm descending here. So I am going to be down like this, which means this is a single root, so I have to pass completely through. So here I go. I'm going crossing the x-axis. Now, to get over here to this other single root, which is next in line, I am going to have to curve back down at some point. That is a single root, so I've got to pass all the way through. So I'm going to curve over somehow. That doesn't look very good. Let's kind of fix that. So up like this. Exactly how high this turns, we don't know, and exactly where it turns left or right, we don't really know. So we don't know this change here. We don't know this vertex, this top portion at this point, and that's fine. So we're just rough sketching. So then I come back down and I've got to go through this one. Alright, so I'm headed down now. Now I've got to pass all the way through this one. This is a single root. So the only way I can do that is if I curve back up somewhere. I don't know exactly where this point is. I don't know exactly where that point is right now, so I'm just rough sketching this thing. And then I have to come up through it, so it's a single root there, and then my end behavior finishes up and to the right, so now I just put my arrow on it. Okay, so that it looks something like this. You could get these points either using a calculator or calculus, but for now we're not going to identify exactly where those occur. But that is the rough sketch. We have a single root at -6. Let's finish labeling those. We have a single root at x equals 3 right there, and we have a single at x equals 6. We need to label these right there. All right, so that one's done. Let's look at one last example. All right, one last example here. We have, this is problem 16 for my students from your assignment section. We have the problem f of x equals x times x squared minus 9 times x squared minus 4. All right, we need to factor this first. It's not factored already because this will factor some more and this will factor some more. All right, so we're actually going to need to do that. So we have x squared minus 9 is a pattern. That's the difference of two squares. And x squared minus 4 is a pattern. It's also the difference of two squares. So if we break this down, we have the x out in front, this x right here. We still have that one there. And then the x squared minus 9 will break down to x plus 3, x minus 3. Okay, that's this part broken down. Difference of two squares. Remember that pattern. And then x squared minus 4 is also a difference of two squares, and that one breaks down to, or factors down is a better way to say that, to x plus 2, x minus 2. All right, so this has been completely factored down to this. So we have a lot going on here, but let's just take it a piece at a time, and it's not that difficult. We actually have 1, 2, 3, 4, 5 single roots. 5 single roots in this case. All right, so 5 single roots. So let's break these down. So we have x equals 0 is one of them. Don't forget about this one right here. If this whole thing is equal to 0, either this is 0, this is 0, this is 0, this is 0, or this is 0. Okay, so don't forget about this one out in front. So I want to get rid of that arrow, so set that equal to 0. So we have x equals 0, or x plus 3 equals 0, or x minus 3 equals 0, or x plus 2 equals 0, or write it down here, x minus 2 equals 0. Okay, so we work all these. X equals 0 is one single root. That's a single root. It's got a power of 1 on it, so it's a single root. This x plus 3 has a power of 1, so we solve it. That's x equals negative 3. It's a single root. X minus 3, solve that one. That gives us x equals positive 3. That's single. X plus 2 equals 0. That gives us x equals negative 2. That's a single. And x minus 2 equals 0, so that's x equals positive 2. All singles. So single, single, single. Okay, I'm going to use that one word single for all of those. All right, so we have, again, 1, 2, 3, 4, 5 different single roots. Okay, 1, 2, 3, 4, and 5. All right. So we factored it, and we have identified the roots, including the type of root. So they're all single roots. Now we need to identify the end behavior. All right. Well, the quick couple of things we can look at. We have 5 single roots. Therefore, we are crossing through the x-axis 5 times. So we can already tell from that this is a 5th degree polynomial. All right, so I'm going to write that here, 5th degree polynomial, or degree 5. All right. If you have 5 zeros, you're crossing through the x-axis 5 times. It's got to be a 5th degree. And if you look at this, we have a power of 1 here, 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 and a power of 1 here, all with an x term inside. So x times x times x times x times x is going to give you an x to the 5th term somewhere. Okay, and it's going to be positive because the leading coefficient out here is positive, right? There's an implied plus there, so this is going to eventually give you an x to the 5th term, and it will be positive. Now remember, this is an odd power, so this is going to have the end behavior. The end behavior is going to be that of the positive cubic. It's going to be the same here and here. So the end behavior looks like that. As x approaches positive infinity, it's going up. As x approaches negative infinity, so going to the left, it's going down. So it's up to the right. So we have up to the right and down to the left. That is our end behavior. So that part's done. Now we just sketch. Okay, this one's not too bad. We're going to have a lot of curving back and forth. It's going to look like a roller coaster when we're done, but it's not too hard to graph because they're all single roots. So let's work left to right and putting these roots in so we don't miss any. I think that's going to be best. So we'll put this one out here at negative 3. All right, that's negative 3 there. Then we have one at negative 2. All right, I'm going to actually take orange here and start checking these. So we've got x equals negative 3 done. We've got x equals negative 2 done. I want to try to do this so we don't get in the way of our graph in a minute. So negative 2, then we have a single at x equals 0 right there. So I'm going to check that that one's done. And then we have the next one would be x equals positive 2. So about right here, positive 2. And then we have one last one. Let me check the x equals positive 2 so we know we did it. And then we have one right here, x equals positive 3, like this. So we'll check that. Okay, our end behavior has to be, I'm going to come over here to the left for my leftmost end behavior, and that's going to be down and to the left like this. Okay, I have a single root at negative 3, so I'm going to go ahead and go through there like this. Now I've got to get to this root next. It's next in order, working left to right, and it's a single root, so I've got to go all the way through the x-axis there. So the only way to get there is come up and curve over like that. So I go through this one. Okay, now I'm headed back down. Now my next root is over here, and it's a single root, so I've got to go all the way through. The only way to get there is to curve back up. How low this dip is, I don't know, but it doesn't matter at this point. So I've gone through that one, my single root at x equals 0. Now I'm headed back up. Now I've got to go through the x-axis here. I've got a 0 here. I've got to pass all the way through. It's a single 0, or single root. So I've got to go back through like this. And then just for fun, I'm going to dip this one down a little more. We don't know how low this dip is. And then I go back up and through there, and then my end behavior looks like that, up and to the right. Okay, so where this rounded top is and this rounded bottom, so this would be a local maximum, local minimum, local maximum, local minimum. Where exactly these are, how high they are, we don't really know, but we know the rough shape of this thing does look like this. Okay, so that finishes that one completely, and we'll call this lesson done. Alright, so I will see you in the next video.